This work is together with 4 other people, Lu and Chao Li, Herbert Spohn, Carlos Tomei, Thomas Trogdon, and you can see a version of this talk you can find on the archive at this particular location. This was a little bit of a new experience for me. As you can see, there was myself in New York, Lu and Chao in Penn State, Herbert Spohn in Munich, Carlos Tomei in Brazil, and Thomas Trogdon on the West Coast. I guess this is what it means to do science in the modern world. Okay, so there is a theme to today's talk, and it's called the duck test. So the duck test goes like this. If it looks like a duck, it walks like a duck, and it quacks like a duck, it's a duck. And this duck test is something which has been used in many different situations, mostly amusing political situations. Okay, so in 1967, Toda introduced the eponymous Toda system with Hamiltonian of this form, HQP, consisting of particles of equal mass m, with positions q, q1, q0, q-1, and so on the line, and with momenta p equals p. Here, A and B in Toda's original system were positive numbers. And these equations then give rise to the corresponding Hamiltonian equations, which have the form Qn dot equals dh by dPn equals 1 over mpn, and Pn dot is minus h by dqn, and has this particular famous form, and this is true for all particles. So Toda's original system was for an infinite set of particles. You eventually get these equations from 2. Now, if you rescale in these equations by setting Qn to BQn and changing time in this particular way, these equations here turned into this following very well-known form: Qn dot equals Pn, Pn dot equals e to the Qn plus 1 minus Qn minus e to the Qn minus Qn minus 1. Now, the equations, these particular equations here are generated by this particular Hamiltonian, where now C can be taken to be any number, not necessarily positive or negative. And so now you've got a system of equations. And of course, how the differential system will behave depends on what boundary conditions you happen to put in, whether you're on the whole line, if n runs over z, or you can, for example, look at these equations where QNs are periodic. PNs will also be periodic for some number capital N, and S, which is sometimes called the stretch parameter, has this particular form. So the first, there was, of course, a lot of work on Toda's original work on Toda's original system for all n running over z. But the first sort of analytical work was based on some numerical work, and people looked at the case where Q is periodic, and then based on this numerical work, first of all, it was Hennen who showed the Toda system with these periodic boundary conditions had n integrals of the motion, where n is this capital N here, and shortly thereafter by Flushka and independently Managov, they also showed that the system had n independent integrals. And in fact, they showed that these two later people, in fact, showed that the system was, in fact, integrable, because they showed that the integrals were independent, and also they Poisson commuted in the natural Poisson structure. This was not something that Hennen had done. He just wrote down the integrals. Now, we are particularly interested in what's called the open Todachain. So again, instead of having these boundary conditions here, we have the following boundary conditions, where you put q0 at minus infinity and qn plus 1 at plus infinity. You put it in here. And then you obtain this particular system of motion here. Qn dot equals Pn, P1 dot equals minus Q1 minus Q2, Pn for n bigger than 2 and less than n minus 1 has this particular form, and P capital N dot looks like this. And this particular system here, the so-called free or, the so-called open Todachain, has this particular Hamiltonian. And the way then Flushka and Manikov and also Henon showed that this particular system was also integrable, and the way that Flushka and Manikov showed the integrability of this particular, the open Toda system, where it showed it could be written in lax pair form by setting an equal to minus bn over 2. Bn is 1/2 of e to the qn minus qn plus 1 over 2. And then they introduced, based on their work on the periodic case, they introduced this matrix here, symmetric matrix n by n, and this particular skew symmetric matrix BF. And then they showed that if qn and pn actually solve this system here, for the open flow, then this matrix here undergoes the so-called lax pair flow, where this is the commutator of the matrix LF with BF. So it's LF LB minus BL, with initial conditions LF at time equal to 0, given by QN at 0 and PN at 0. So that these entries here, these A's and B's, then take on initial values given by Pn 0 and Qn at 0. So it immediately follows, as we all know from this lax pair form, that the eigenvalues of LF in time are constant and equal to the eigenvalues of the initial matrix, which are lambda 1, lambda 2, and lower, and lambda n, which we are ordering in this particular fashion. And so these provide in constants of the motion for the open Toda lattice. And eventually that means that the system is Liouville integrable. So in other words, these particular numbers, these integral, these eigenvalues here, lambda 1, lambda 2, and so constant of the motion, and that they Poisson commute and they are independent. So that's sort of the early story of the Toda lattice. People were interested, people like Flushka and also Manikov, and also Hennen were interested when in fact you have an infinite number of particles, and then there is more than just point spectrum, there's continuous spectrum, and it was understood that system was also integrable in some very natural sense. But we want to focus on this open Toda lattice, because subsequently Jürgen Moses showed how to use this lax pair form to solve the Toda equations. So these equations over here. Showed how to solve these equations explicitly in terms of rational functions of exponentials. Furthermore, Moses showed that the system had the following remarkable long-term scattering behavior. In other words, the momenta were eventually, this T is, this is an error, this T shouldn't be there. Eventually, the momenta became constant with some exponential decay rate, and the particles Q and T were moving linearly with these momenta, and there was a phase shift, and again an exponentially small error term as t becomes large. And these numbers here, this alpha n plus minus t, are related to the eigenvalues of this matrix, which are these numbers lambda 1, lambda 2. So alpha n plus is minus 2 lambda n, and alpha n minus is this particular quantity. And most remarkably, Moser was able to compute this phase shift in this explicit form. So beta n plus minus beta n minus n plus 1 minus is given by this explicit form here, which is expressed in terms of the eigenvalues of the initial matrix. So you notice the following is that the system works in the following way. So the velocity of this particle here, as t goes to minus infinity, is then transferred to the particle qn as time t goes to infinity. For example, if I take little n here equal to 1, then we're speaking about the particle q capital N, and the particle q capital N has a particular velocity as time goes to minus infinity, which is then transferred to the first particle Q1. And the interesting thing then is that there's a phase shift, which is given by this difference over here. Now, this was a remarkable computation, and interestingly, Moser never computed these numbers beta n plus minus explicitly, but he was able to compute their difference. The computation of these numbers were actually obtained only later by a number of people. So just stopping back for a moment, when I came across this formula in the 1970s, when I first came to Courant, when I came across this phase shift formula, which is equivalent to knowing the scattering shifts for, or equivalently the scattering matrix for the system, I was really astounded by that, because here we were looking at an explicit computation for an n particle system. Now, my background was in general abstract scattering theory, and the idea that you could actually compute something like this was very remarkable to me. So I asked Moser how this was possible, and Moser's response was somewhat mysterious. He said the following: every scattering system is integrable. So it took me some time to understand what Moser what Moser was saying. So just to repeat this, I found this formula very remarkable. I mean, I'd never conceived that you could take a bona fide n particle system and compute something like the scattering matrix explicitly. Nevertheless, for Moser, this was sort of an obvious thing. So what did Moser have in mind? Suppose one has the solution of a Hamiltonian system, Q2, Qt, Pt, looking like this in R2, 2n, with some Hamiltonian H, and with the property that the momenta become constant with some decay rate, and the positions of the particles move linearly with velocity, which is given by the limiting value of the momentum. And it behaves like this for some constants Q infinity and P infinity. So let UT Q0 P0 be QT PT, which is this quantity up here. It's the solution of the system with this initial data. And let UT super 0 Q0 P0 be the solution of the free particle system with Hamiltonian HC QP P squared over T, P squared over 2. So in other words, P0T equals P0 times 0. And so this is the exact solution of this trivial system. Now, what Moses' observation is that suppose you look at the composition of the solution of the free system with the interacting system with some initial data Q0, P0. Then as time goes on, the solution of the full system Qt is given by Q infinity with P infinity plus little o1, which is this quantity up here. And it has momenta P infinity with nth term little o1 of t. But because of this behavior of the free system, at time minus t, you must take the position of the system at the time and then take off this particular quantity. That's exactly what you learn here. So you've got this particular momentum at that time, and you must take that off. So what you have here, because you're using minus t, so you take that, and this momenta here under the free system remains the same. Then the P infinity of t cancels with this P infinity of t, so you've got Q infinity as little o1 plus P infinity is plus little o of 1 over t, and as t goes to infinity, this has got a limit, Q infinity, P infinity. So the way to say this, if you look at the composition of u0 minus t with ut, this has a limit, which we call the wave operator. But then once you have this fact, and you look at this composition, and you use the law for the group law for the propagators, u0, and for ut, so uts is u of t plus s, and this quantity is just u of minus t. So now you let t go to infinity. On the left-hand side, you get w composed with us. And here, as you let t go infinity, this also goes to w, so you get this relationship here. Or if w inverse exists, that you have to do separately, you see that us, which is the solution of the full interacting system, is just this conjugation of the original free system. But because this combination here is symplectic for all t, that means that w, which is the limit of the symplectic value, will also be symplectic. And once w is symplectic, w inverse is symplectic. So what 12 is telling you is that the interacting system, which is given by us, is symplectically equivalent to the free system, and hence it is completely integrable. So indeed, if these numbers here, or these functions here, alpha 1 to alpha n, are commuting integrals for the free system, then you define beta I to be alpha I composed with w. These are necessarily commuting integrals for the interacting system. If you take beta I composed with ut, which is the solution of the interacting system at time t, you substitute for beta I, you substitute alpha I composed with w, then you get this w composed as ut, and you use this intertwining relationship. You replace w composed with ut with u0, t composed with w, then this is just some initial data, and you've got some initial data being evolved under the free system and acting on and being inserted into the constant motion alpha I. So this is constant. So these quantities beta I are constant of the motion for the integrable system, for the interacting system. And as w is symplectic, the beta i's, which are alpha I composed with w, alpha j composed with w, and because w is symplectic, it comes out of the Poisson brackets. So this is just the Poisson bracket of alpha I, alpha j with w, and that's just 0. So in other words, you immediately are going to get commuting integrals for the original system. So the way to say this is that, and say it more generally, and this brings us back to the theme for today's talk, is that the above calculation shows it more generally that, quote, if a system behaves like an integrable system, in the sense we made clear B before, then it actually is an integrable system. Or as in the famous duck test, if it looks like a duck, it walks like a duck, and quacks like a duck, it is a duck. So, and this is a very general situation. I'll give some illustrations in a moment. So referring back to Moses' long time estimate 9, so let me just go back for a moment here. So if we see Moses' calculation for the open Toda lattice, we see that this, as I say, this T shouldn't be here, that the momenta become constant and the positions just evolve linearly. So it looks like an integrable system with some sharp errors. So hence it actually has to be an integrable system. And that was the explanation of Moses' rather mysterious comment. So there is an interesting remark here, as that from this duck test, we learn that there is an interesting catch-22 in the problem. I mean, I don't know if catch-22 has the same meaning in Russia that it has in the US, but it's a famous book. And what is catch-22? It says that if you're interested in something which we can call A, to get A, you need to have B. But in order to have B, you have to have A. So you're in a closed loop there and you can't get going. So what's the catch-22 here? It means that we could not have derived by any means, utilizing any and all dynamical tools, the asymptotic behavior of the system, unless it was integrable in the first place. Because no matter how you derived this asymptotic behavior, that would immediately imply that the system is integrable using Moses' argument. So that's the catch-22. You might be the kind of person who says, look, I don't care about all these integrable ideas. Let me just use my hands and a piece of paper and a pencil, and I'm going to just show you how the system behaves. And you won't be able to compute that asymptotic behavior, no matter how hard you try, without the background fact that, in fact, you would not have succeeded if the problem was not integrable in the first place. So now Moses' argument can be used to prove the integrability of a variety of dynamical systems. For example, Moses' proof of the integrability of a charged particle in a dipole field. This is a famous so-called Stormer problem in another direction. Myself and Ginger showed, contrary to expectation, that the perturbed defocusing nonlinear Schrodinger equation, which looks like this, IQT plus QXX minus 2 mod Q squared Q minus epsilon K of Q squared Q is 0 on the line, is in fact integrable for some epsilon 0 and all epsilon less than equal to epsilon 0, provided K of Q squared is of order mod Q to the L as Q goes to 0 for some suitably large L. So in fact, this came as a surprise to us that, in fact, when you perturb NLS on the line, in a very general way, in fact, remains integrable. And the proof of this is based on Moses' ideas. So what you have to do is you have to prove that this particular system, when epsilon is non-zero, behaves like the integrable NLS equation. Now, getting to what we're actually going to talk about, in this talk we consider Toda's original system 5 in the fixed end case with C not equal to 0. So we're looking at this particular Hamiltonian system. Of course, when C is 0, we have the integrable open Toda lattice with n particles. But now we're interested in the situation when C is not equal to 0. And this gives rise to the Hamiltonian equations, which look like this. It's exactly the same as before, except you now have this instant, this constant term C in here. Now, something which needs to be emphasized, and that is that boundary conditions really are a reflection of physical forces. And you can see that over here, that if you look at this term here in the Hamiltonian, you sum it up, it looks like this. And so we can think of this Hamiltonian as the Hamiltonian of a lattice of particles, Q1 to Qn, but now there are external forces on the endpoints given by this potential term here, this external potential term here. So when C is bigger than 0, you see that the effect of this potential on the first particle is given by the derivative of this quantity with respect to Q1, which gives you minus C, and the force on the other end, Qn, is given by plus C. So you see that when C is positive, the first particle is being pulled to the left, whereas the other end, the particle at the other end, is being pulled to the right when C is positive. So it stretches the lattice, and when C is less than 0, they compress the lattice. So this is a very natural system to look at, and the point which one really wants to emphasize here, which is something which should always be emphasized, that boundary conditions really are a reflection of how external forces act on a particular system of interest. Here it's either stretching or compressing the system. So the system HC arose naturally in the study by Herbert Spohn of the statistical mechanics of the Toda lattice. There's more information about this in the archive principle. So Herbert suggested that we begin looking at this, and we began looking at it, of course, from a numerical point of view. So I'm going to lay out some numerical calculations now. And the numerical calculations suggest strongly that in the case C bigger than 0, HC is in fact integrable. And indeed, our main result is to show, using Moses' integrability argument, that this is indeed the case. In the case C less than 0, we will argue below that the numerical calculations suggest that also in this case there is some integral structure or near integrable structure, but the problem here is very interesting and remains open. So just let me be absolutely clear. The numerics which I'm going to show you will suggest very strongly that when the external forces are stretching the system, it will be completely integrable. But in the case when C is less than 0, there are hints that there is integrability in the problem, but it's an open and very interesting problem to actually show that that is the case. So as a benchmark, in figure 1, which is this figure 1, this displays solution be open Toda lattice. That is when C equals 0. There are 20 particles. You have random initial conditions. The blue are the initial positions. The red are the initial momenta. And you see here that as time goes on, the positions move linearly in time, and the momenta sort themselves out and eventually become constant in time. Now, just as a parenthetical remark, you look at this thing over here, and then there's some kind of switch which goes on in your mind, at least in my mind, that when you look at these calculations, you begin to give a sort of anthropomorphic quality to these particles. You begin asking yourself, I know it's sort of nonsense, but nevertheless, you find yourself asking, how do these particles know how to sort themselves out and eventually go? And so what is driving these particles? Of course, it's the mathematics, but somehow your mind switches and you begin to if you stop thinking of them as being just mathematical, but you think of them as particles with sort of a life of their own, and you begin to have this non-scientific sense that the particles are alive and interacting and sorting themselves out. So that's just an impression you get when you make these calculations. Now we turn on C equal to 1. So now we're in the case where the system is stretching. Again, 20 particles, you have random initial data, and you see the following. Again, you see that all the particles from 2 up to n minus 1 eventually have momenta which sort themselves out and eventually become constant. However, the last particle here moves off, has a velocity which is eventually growing linearly, and the first particle positively, and the first particle has a velocity which is also growing linearly but in the other direction. This has the effect that the particles from particle 2 up to particle n minus 1 will eventually move linearly in time because of this behavior, whereas the positions will now move, the last particle will move quadratically because the velocity is growing linearly, and similarly for the first particle, which is going in the other direction. So you begin to get a very strong idea here that what the system with C positive is doing is that it's splitting apart particles 1 and n, the first and the last particle, separate off from an inner core of particles from 2 to n minus 1. The particle 2 to n minus 1 lose contact with the particles 1 and n, and they behave like an open Toda lattice, whereas the other particles, which would give you just an independent system of two particles, are moving off in an integrable fashion. So in other words, in terms of the duck test, we're seeing that the system is behaving as if there is an inner core which is completely integrable, and two independent particles which are themselves an independent integrable system. So you have a disjoint union of two integrable systems, and hence you can see from the point of view of the duck test is that the system is behaving like an integrable system, but not the same integrable system that you have for C equal to 0. You also have this new integrable system. Now, this is saying again what I've just said in words. Here's the formula for particles from 2 to n minus 1. The momenta are growing, constant. The velocities are growing linearly, but P1 is shooting off linearly in the negative direction, which makes the velocity go off at the quadratic rate. And similarly for the last particle, but now in the other direction. So just to repeat myself, this suggests that the solution of HC equations behave like a solution of n particles consisting of a Toda lattice in a core decoupled from a pair of decoupled particles, which are evolving in this particular way. Any system which looks like this is a system of two degrees of freedom, which is integrable. So such a system of n particles is clearly integrable, and what we actually show is that solutions of the perturbed system indeed behave asymptotically like solutions of this decoupled system, and hence in the view of Moses' observation, the perturbed system is integrable. Now, I just want to read this first, and then I'll show you the pictures and we'll come back to it. So figures 3, 4, and 5 display the solutions of the perturbed Toda lattice HC with C equal to minus 1 at different initial data. In all three cases, the solution Q-N-T appears to involve almost periodically in time, modulo a slight gradient The gradient arises from the fact that the total momentum is conserved, and so that means that the center of mass moves linearly. However, for some unexplained reason, all the particles come together at essentially periodic intervals, T1, T2, and so the position of the nth particle, little n, at time tk, all the particles come together, so all these q are essentially equal. So qn is just the average of these, and because this is moving linearly, you see at these times, the particles are moving in a linear fashion. This is a bit of a mouthful, but I'm going to show you the pictures and I'll come back to it. Now, the important point to notice is that in the first two cases, this behavior persists at least up to times t equals 300, but in the third case, the almost periodicity begins to unravel after t equals 200. So here is the first case. So c is minus 1. You have these positions and these initial momenta. So focus on the behavior of the position. So you see there is this slight decline, but the particles are appearing to move almost periodically in time. Eventually, when you get to time equals 300, the picture begins to unravel. So you see now what I was saying is that the total momentum is conserved so that the center of mass moves linearly. But because all the particles come together at these times here, it means that the position of all the particles must then lie on this line here. Now, to show that this type of picture is not just a fluke, let's look at the same situation, c equals 1, but now with different initial conditions. And the same phenomenon shows up again. There's a line, and the particles move on the line, but almost periodically it would appear. And they all come together at these particular times over here. And again, things are starting to unravel when you get up to around 300. Now, final case is again, you see a similar phenomenon, but n equals 20, c equals minus 1, and you have, again, the motion along this line. Particles are coming together, but you already see here around 200, it's beginning to unravel. So let me just say that again one more time. So figures 3, 4, and 5 for c equals minus 1. In all three cases, the solutions appear to evolve almost periodically in time, modulo a slight gradient. The gradient, the slight gradient follows from the fact that the total momentum is conserved, and for some strange reason, all the particles are coming together. Things unravel in one case for time, after time about 300, but in the other case, 200. So these calculations in the case C negative bring to mind the celebrated computations of Fermi, Pastor, Ulam, and Tsingo, in which the authors, anticipating ergodicity, found unexpectedly almost periodic behavior in the solutions of a particular nonlinear lattice system. This means that in some sense, the system was remembering its past, and the only way a mechanical system can remember its past is if it has many integrals of the motion. Now again, our minds are switching, as it were. We're looking at these particles, we can't help, at least I can't help, you begin to think of these particles as little living things which are interacting with each other, and how can these little living things remember their past? It's coming back to its original form. Well, the way it does it, this mechanical system, is by having many integrals of the motion. So in this way, the discovery was viewed as strong evidence for integrability. So, and led eventually and famously to the discovery about Kruskal and Zabusky and Gardner, Green, Kruskal, Miura, that the KDV equation is completely integrable. Just to run that through again, this is a very familiar story. It was the almost periodicity of the system which led people to begin to suspect that there had to be a lot of integrals of the motion. Now, over the years, as the power of computers grew, it became clear that Fermi, Pastor, Ulam, and Singer had just not run their equation long enough. With longer computations, they would have found that the almost periodicity unraveled and ergodicity did emerge. So there is a very interesting understanding of the experiments of Fermi, Pastor, and Ulam. Many people have spent a great deal of time trying to understand what was going on there, but there's a very nice, very recent preprint on the archive by Galan, Pono, and Rink at this address, which works in the following way. So the lattice equations for unidirectional lattice waves can be written schematically in the form x dot equals v of x plus something of order h squared, where h squared is a continuum limit parameter on the lattice. So when h squared goes to 0, you go into a continuum situation. But in this picture, this equation, y dot equals vy, is in fact KdV. So it follows that solutions of the lattice equation behaves like the integral KdV equation for times t of order h to the minus 2. In other words, when this term here, th squared, is of order 1. When x of t begins to diverge from y of t. So what it means that the lattice has many h squared accurate integrals up to times of order h to the minus 2. It turns out, however, that the near integrability persists for much longer times t of order h to the minus 4. And this they elegantly explain by showing that, in fact, x of t solves a system of the following form: x dot equals w of x plus order h to the 4th. But now this system here is a solution of the KdV hierarchy, a particular equation in the hierarchy, and also completely integrable. So it looks like an integrable system up to an error h to the 4th. So we are led to the following speculation. Is the Fermi, Pastor, Ulam, Singer problem a guide to what we see for c less than 0? Fermi et al. Raises the issue of whether there is some integrable system associated with the lattice which ascribes the solutions of the lattice equation to high accuracy for large but infinite times. And I remind you that when we looked at those figures 3, 4, and 5, the behavior was almost periodic up to at times t equals about 300, but then began to unravel. So in this way, for large time, the system would have excellent but not perfect memory. So the problem is extremely interesting, extremely intriguing, and it's completely open. It would be, I believe, it would be a major result to understand this particular problem, because you won't be able to do it without introducing some really new idea. So just as a remark, the Fermi-Pastor-Ulam-Tsingo paradox, as it is called, is a modern illustration of the interesting phenomenon that sometimes science makes progress not because of the accuracy of its instruments, but rather because of their inaccuracy. If computers in the 1950s could have made longer calculations, would KdV have been discovered as an integrable system? If Copernicus had more accurate instruments sensitive to the fluctuation of the planetary orbits, would Kepler have been able to come up with his perfect laws? So the integrability of HC with C bigger than 0 is proved in steps. In the first steps, we proved that solutions of 15, 15 is our system here. So it's this particular system with HC, so these are equations 15. So the first step is elementary fact, or very standard fact, is that the solutions of 15 generated by HC with some initial data are unique and exist globally. The same is true for C less than 0, but we are only interested in C bigger than 0. Now, remember, the way the whole thing is operating is to show that the system is going to break apart with particles 1 and capital N separating off from the remaining particles Q2 to Qn minus 1. And so what you actually have to show was when T becomes large, the solutions of the interacting system look, I have the following form, of course, Qn is always equal to, Qn dot's always equal to Pn, but now particle 2 behaves like the free particle at the end of the system, but it now has an error term which is going to be which is going to decay super exponentially. Particles from 3 to n minus 2 will just be behaving as pure Toda particles, and particle P n minus 1 behaves in this particular fashion, where again you have this error term here, which is super exponential. So the inner core is, if these terms were 0, if O2 was 0 and ON minus was 0, it would be just behaving like a system, an open Toda lattice with particles 2 up to n minus 1. So it almost looks like this, and you have these super exponential terms over here. What happens to the two remaining particles, Q1 and Qn, is that Q1 goes shooting off to minus infinity, and Qn goes shooting off to plus infinity and separate off from the system. The first thing is to show that, in fact, the inner core almost looks like the free or inner core. What we then obtain is that, so this shows that you get the separation, but then you actually obtain precise asymptotics for the inner core. And here you look at the system, which is the decoupled system. Here is an inner core, which is a pure Toda system, and here you've got a decoupled system of forces acting on the first and the last particle. And then you finally consider the solution. So UT hat is a solution of this decoupled system. And then finally, you look at what we call our free system, which are just free particles, together with these four forces on particles 1 and particle n. In step 4, you show that the solution of 15 behave like these. This is the full system, behave like free particles. And the convergence is sufficiently rapid so that Moses' argument applies. So from a technical point of view, this is a solution of the full interacting system. This is a solution of the free particles. And you show that this wave operator exists, so you know that it means that the system looks like these free particles. On the other hand, you prove that this wave operator exists. So this is the decoupled system consisting of an inner core together with decoupled particles 1 and n, and they also look like this free system. So this wave operator and this operator exists, and then you prove that this operator is invertible, and you look at this composition, and this composition gives you your intertwining operator between your full system and the system here, which is built up out of the inner core and 2 decoupled particles at the end. The final step is we show how to use W to construct action angle variables for HC, and also how to write the equation 15 generated by HC in lax pair form. People might think, well, have we really shown it's completely integrable in the classical sense? You would want to know that you actually have action angle variables you can construct for the interacting system, and also you can write it in a Laxper form. Finally, let me just say, as a technical comment, obviously I'm not going to go through all the details. The key thing is to prove, this should be a capital N here, is that these terms here are super exponentially small. That is the key technical thing that you really have to do. And that is done in a bootstrap argument. You prove it has so much decay, then more decay, and more. But the first step is a following very elementary calculation, which is utilizing the fact that this part of the Hamiltonian is strictly positive. So let's, for a particular flow, the Hamiltonian here is a constant which you call H0. You look at P1 minus, this should be a capital N here. That's, of course, less equal to this, which is less equal to sum of the momenta. And if you plug this piece here into here, you see this is less equal to H0 minus this quantity over here. And then that means you led to this differential identity, which you can integrate. And what this particular inequality does, which is this key elementary inequality, it shows that the particles Q1 and Qn can move apart, but they can't move apart too far. And that is what provides the key control for the system.